All right, so yesterday we talked about differential equations. Where's my... Okay, eventually I'll be able to do this. Recording. Again, please, mic's on so that I can talk to you. All right, so yesterday we started talking about differential equations. We said a differential equation is an equation in which the variable is essentially the function, right? So we have an unknown function and unknown function and its derivatives. And its derivatives. And if we want to use differential, and the reason that we want to look at differential equations is that they help us model a lot of real life situations. Now, if we want to check that a function is a solution of a differential equation, we're going to do this in the same exact way that we do it with normal equation, which is basically to say, okay, well, if this thing is a solution to my differential equation, then if I plug the function into the differential equation, the equation should still be verified, right? So what we're going to do in the first part today is to check that a function is a solution of a given differential equation. So I'll have an example, which is to show that blah, 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 is a solution of the differential equation below. So what am I going to look at? So I'm going to show that y, which is equal to 4e to the negative 3x plus 1 is a solution of the differential equation. Y prime is equal to minus 3y plus 3. Right? And so if we want to do something like this, all that we have to do is, well, plug this function for y into my differential equation. So I'm going to verify the left-hand side and the right-hand side, and then I'm going to see if they match. So on the left-hand side, if I plug in my function, I'm going to have that y prime would be equal to 4e to the minus 3x plus 1 prime, right? And if I find the derivative of this function, I'm going to get, for the first term, I'll get 4 times the derivative of e to the minus 3x. So the derivative of e to the minus 3x is going to be e to the minus 3x times negative 3 by using chain rule, and the second term becomes 0, right? So that means if I simplify, I'm going to get minus 12 times e to the minus 3x plus 0. Hands up if you understand what I just did. All right, and then in the second part, I'm going to check the right-hand side. So I'm going to have minus 3 times y plus 3. So I have that this is minus 3 times 4e to the minus 3x plus 1. So this is just y, so that's why I'm replacing it there, plus 3, which is equal to minus 12, if I distribute, minus 12 e to the minus 3x. And then minus 3 times plus 1 is minus 3. And then plus 3 means these two cancel. And I get minus 12 e to the negative 3x. Yes, Michael, there's a question.
No, my bad, sir. I just
All right,
forgot to put it up.
All right, okay. And so then you get these two things which are the same. That means that the left-hand side is equal to the right-hand side. And so my equation is verified, and y is actually a solution of the differential equation. Does everybody understand this?
Mm-hmm.
Okay, good. So we have that the left-hand side and the right-hand side are the same. This is a solution of the differential equation, and then we're done. Okay, let's do another example. I'll give you a couple of minutes to solve it on your own, so verify it yourself, and then we'll do something else. For example, which is verify, what is it? Show that every function of the form what is this? Y is equal to some constant times e to the minus x squared is a solution of the differential equation, and the differential equation here is going to be, what is it? Y prime is equal to minus 2x times y. Okay, so in this case, I want you to verify that every function of this type is going to be a solution of the equation that is written on the right. Okay, so you have 2 minutes to solve that problem. Michael, is that your hand up now?
Yeah.
Okay, good.
Sorry, in the first part on the left-hand side, why did you plug in -3? Like, how did that work?
This one?
Yeah.
Okay, so that's because it's a chain rule, right? Like if I'm differentiating for e to the minus 3x, that's
Okay,
4 times the derivative of the outside, which is e to the u, and then multiplied by the derivative of the inside, which is just
yeah,
minus.
it is. All right, thank you.
Yeah, okay. All right, so 2 minutes, and I'll give the solution to the second problem. Okay, so at this point, you should have tried to evaluate, just like in the first example, first the left-hand side and then the right-hand side. Okay, if we try to do that, so I'm going to do left-hand side over here. For the derivative of for the left-hand side, you're trying to evaluate the derivative of the function, which is y prime. And that means that we would be finding the derivative of c e to the minus x squared. What's the derivative of this going to be?
Two x c e to the negative x squared.
Okay, so we have negative 2, oops, there you go. Negative 2x, which is the derivative of the inside, times the derivative of the outside. So that's c e to the power of the same thing that we started with, right? So which is minus x squared. Does everybody understand that? Show of hands for those of you who got that for the left-hand side. Okay. So this is what we get for the left-hand side. Now, it's going to become really important, of course, that if we're doing differential equations, we know how to find derivatives properly. So make sure that you have at the back of your mind that you need to use sometimes chain rule, and sometimes you need to use product or quotient rule, depending on what you're trying to evaluate here. Okay, so then we're going to have that the right-hand side is minus 2x times y, which is equal to minus 2x times the expression that I had for y, which was c e to the minus 2x squared. And so these two things are the same as well, right? So these two things are the same, which means that the left-hand side...
Only x squared, no?
Oh, yes, only x squared, sorry. Oh, of course. There you go. So the left-hand side is equal to the right-hand side. And this is a solution of the differential equation. Can you raise your hand if you understand, please? Okay, so 14 hands, I call that a success out of 18. If you don't have any questions now, if you don't understand fully, now's the time to raise your hand if you have any questions to ask. Okay, so for the next one, I'm going to ask you to, again, do the same thing. Verify. So verify. Same for. The function is going to be y of t. So y is equal to 3/4 plus some constant c divided by t squared. And the differential equation is 2 times t times y prime plus 4 times t, no, 4 times y, sorry, is equal to 3. Okay, so you need to verify that the left-hand side is equal to the right-hand side for this particular choice of the function y. Okay, so I'll give you again 2 minutes in order to solve that. Now, we have to actually evaluate the derivative of this function. So I'll have 2 times t times derivative of 3/4 is just 0, and derivative of c over t squared is going to be minus 2c over t to the power of 3, right? And that's because this is the same as c times t to the power of -2. Do I have any questions about that? All right. And so what I'm going to do is now distribute the 4 onto both of these terms, because I know that eventually I'm going to have to simplify something, right? I'm looking to see if the final result over here is going to be equal to 3. So I'm going to simplify some things, and then hopefully I'll get the result 3 at the end. So I'll have plus 4 times 3/4 plus 4 times c over t squared. Now, at this point, 2 times t times 0 is, well, 0. And then I can actually distribute the 2 into this term, which means that I get minus 4 times t times c divided by t to the power of 3. Plus 4 times 3/4 is going to be just 3. And then plus 4c over t to the power of 2. Now, that's actually pretty nice because one of the t's at the numerator that I have in this fraction cancels with one of the ones that I have at the denominator. This means that this is 4 times c over t squared, which is the same as this term. And then I can just cancel those two terms with one another, right? So then I'll have this one cancels with that one, and my final result is actually equal to 3, right? So this tells me that the right-hand side is equal to the left-hand side, and my equation is, my function is a solution of this differential equation. Do I have any questions? No questions?
Yeah.
I'm kind of lost.
Oh, where?
So for the right-hand side, you put 3. Is that because it's like on the right side of the equal sign?
Yeah, that's because this is the right-hand side.
So what did you do with the left-hand side? That's where I'm confused.
Okay, so for the left-hand side, what I'm doing is just plugging in the value of y, right? So like here, this is y, but it has to be differentiated. So that's why there's a prime. And here, I replaced by y, but I'm not going to differentiate that term because this one doesn't have a prime in front.
Okay.
Right? At this point, I'm just differentiating. So I'm actually finding the derivative of the terms that I have inside that bracket. And in this term, I'm just distributing because I know that eventually I'm going to have to simplify.
Okay, perfect. Thank you.
Make sense? Michael had a question as well, or does that answer it?
Yeah, that answers it.
Okay, good. All right, so it's really just a matter of plugging the value of the function into your equation and then differentiating whatever you have to differentiate. So you can think about it in the same way as you think of equations that involve x, right? So in general, when you have like, I don't know, 4 that you plug into an equation, you have to then apply some functions to that number that you plug into the equation, right? So that means if there's a square, then you take 4 squared. Well, in this case, what you're applying is a derivative. So if you have a function, then now you have a function prime. Does that make sense? be like doing a little bit more operations on those terms. All right. Everybody that understands, please raise your hand. Okay, good. Good, that looks like most of you answered yes. Okay, now, in the previous page and in this page, you may have realized that you had, for example, here, show that every function of the form c times e to the x squared is a solution of this equation. What that means is that you have a function, but that function that you have has also a constant in front that is not necessarily, it doesn't necessarily have a specific value, right? So for example, here you didn't have that c was equal to 2, or it was equal to 3, or it was equal to a given value. You have that it can be any value of c that's possible, right? Same thing over here, you have a given function, but that function doesn't depend on the value of c. So c over here could be equal to 2, 3, -1, 4, pi, whatever it is, right? And regardless of that value, these terms ended up canceling out. So that means that this value over here doesn't affect whether my function is a solution to the differential equation. Now that is because this function over here is what we call a general solution. So you might remember in the first section that we covered in this class that if we had, what was it? So if we had the derivative of a given function, we were only able to find the general solution to my differential equation, right? So for example, if I had the derivative of something, I could have found like this or something like this. And then only after I was given an actual value for the function at a given point could I say, oh, actually the one single function that I'm looking for is the one that passes through that point. Who remembers something like this? Not that many people. Okay, so essentially that means is if you have the derivative of a function, you only have an expression for how the function is changing, but you don't necessarily have exactly the value of the function at a given point. So if you're given the derivative, you might be able to determine how the function is changing, but if you want to know what the function actually is, you might need to be given a little bit of extra information, which is why we talked about having initial conditions, right? So like something like this, the way that we called it was that we said, okay, this is an initial condition. And based on the initial condition, we were able to specify the one solution that was actually a solution for a specific problem. So I'm going to define this couple of things. We have that. So I'm going to first put this. So note that the function, and this was the function y is equal to, whoops, y equals to c times e to the minus x squared is not a unique function, right? So is not unique. So that means it's not just one function, right? Instead, it's a family of functions. So it's a type of function. So essentially what this means is the function y is equal to c times e to the minus x squared is every function that is of the form some constant times e to the minus x squared. But that constant might be different from one value or another. So what we say is that it actually represents a family of functions. Right? So for each value of c, you get a different function. Right? So for example, the function 1 times e to the minus x squared is not the same as the function 3 times e to the minus x squared, and it's also not the same as minus 4 times e to the minus x squared. Each one of them is different, but they are all solutions of the differential equation that we solved just earlier. So that's because we have some we have some functions that are general solutions of differential equations, and then we have some that are particular solutions to differential equations when you're given also an initial condition, right? So the family of functions that verifies a differential equation, which we denote dE, is called the general solution of the differential equation. Okay, so we talked about this even in the first chapter of the class. We said if we know the derivative of a function, we are able to find the type of function that is going to give me that derivative, but I'm not necessarily able to find the specific one function that I'm looking for, right? If I want that, I need something else, right? And that something else is, in general, an initial condition. So the unique function that additionally satisfies an initial condition, IC, is called a particular solution. Okay, so now we have two things. We have initial condition, and we have a general solution which satisfies just the differential equation, and we have a particular solution which satisfies the initial condition as well. Okay. Do I have any questions about this? Okay. So, as an example, we're going to start by finding the particular solution to problems for which we already know the general solution. So, example, solve the following initial value problem. Okay, so initial value problem, we already talked about this at the beginning of the semester as well. When I say initial value problem over here, what that means is initial value problem is the same as a differential equation and an initial condition, right? So in these cases, I can actually find just the one function that satisfies both of these things at the same time. All right, so the initial value problem that I'm going to ask you to solve in this case is the following. First, I need a function that satisfies the following differential equation. So y prime is equal to -2 times x times y. Okay, and then I need this function to also verify that y of 0 is equal to 4. So that means this over here is my differential equation, whereas this is my initial condition. Can you please raise your hand if you remember us having some differential equations and initial conditions at the beginning of the semester? Beginning of the semester seems to be really far. Okay, there you go. All right. Okay, so I have to solve the equation y prime is equal to -2 times x times y, and the initial condition y of 0 is equal to 4. I'm asking you to solve this differential equation, but I still haven't taught you how to solve differential equations. According to you, what do you need to do in this case? How would you start?
Evaluate to get the function of y.
Sorry?
Evaluate the d.
We need to evaluate the d. We need to solve the d, but I haven't given you any method to solve differential equations yet.
Find the antiderivative of y prime.
We would have to find the antiderivative, but it's going to be difficult since we can't integrate the left-hand side and the right-hand side, because we'll have to find we'll end up finding y on the left-hand side, but then we'll also be integrating it on the right-hand side, right? So that doesn't really help me that much. Is this a differential equation that you've already seen? Has anybody seen this differential equation before? Vicente, you have your hand up. Oh, I thought you had an answer for me.
My bad.
Is this a differential equation that might look familiar? Maybe like exactly the one that we solved at the beginning of the class? No? Okay, so we have this differential equation over here, right? And what we said is the solution of a differential equation that looks like this is of this form. Who understands that? So we said any function of this form is a solution of the differential equation y prime is equal to minus 2xy. So what I can start by saying is, okay, well, I don't know exactly what the function is, but I know that it will look like this. So I know that it will be of this form, right? So I know, here we go. I know that any function of the form y is equal to c times e to the minus x squared is a solution of this differential equation. Is a solution of this differential equation. Right? So this is what we showed at the beginning. You're just given already the solution, and then and you know that it verifies it. So now essentially we've been told, okay, well, this is a solution of the first part of the problem. Now all that you need to do is to verify that the second part of the problem is also verified. How could I do that? Any ideas? So what is the only thing that I have left to find in this case? Anyone?
C.
C is the only thing that I don't know for this function, right? E to the minus x squared, that's already a function. But the c that I have over here, I still don't know what its value is going to be. So that means that I'm going to plug into the initial condition and figure out what the value of c is going to be. So I have y of 0 has to be equal to c times e to the minus 0 squared, which is equal to c times 1, times 1, which is equal to c. And I know that y of 0 has to be equal to 4, which means that c is equal to 4. Does anybody understand this? Can I see a show of hands for those of you who do not understand it? Okay. Maybe that's the question that I need to be asking. So essentially what I have is, I know that any function of the form c times e to the minus x squared is going to solve this equation, right? So I already know that whatever function I'm going to find is going to be of this form, right? So it's going to be some constant times e to the minus x squared, and that way I will guarantee that my function satisfies the equation y prime is equal to negative 2x times y. Does everybody understand that? Who does not understand that part?
What does the e have to do with the differential equation that you gave us?
I'm sorry, what?
Like you gave us y prime equals negative 2xy.
Mm-hmm.
So what does that have to do with the e?
With this one?
Yeah.
Okay, well, what that has to do is I said, okay, well, you don't have a technique to solve the differential equation yet, right? So what I told you is you already know a solution of the differential equation because I told you before to verify that this type of function was a solution to the differential equation.
Okay.
Right? So essentially what I'm saying is, okay, now you know that this type of function solves the differential equation. It's a solution of the differential equation. So now you have a type of function that solves the differential equation, right? You know that every function of the form, some constant times e to the minus x squared is going to verify the differential equation that you have here.
Okay.
Now, if we want to look at the one particular function, the one function that satisfies not only the differential equation, but also the initial condition, we're going to have to figure out what the actual value of c is going to be.
Okay.
Does that make sense?
Mm-hmm.
Is there anybody that still does not understand this? Show of hands.
But how did you get to c equals 4?
Okay, so then I use this initial condition, right? So what I do is I first plug in 0 into the form of the function that I have, right? So I'm just saying, I'm just saying, okay, if I plug 0 into this one, okay, guys, I'm clearly not being very clear today. So I know that my function has to be of this form. Yeah. So that means that if I evaluate y of 0, it should be, oops. If I evaluate y of 0, it should be equal to c times e to the minus x, which is 0 squared. All right. And if I do that, that means that I'm going to get c times e to the power of 0, which is just c times 1. And so that means that I know that y of 0 is going to be equal to c. Does everybody understand that? Is there anybody that does not understand this part? So then I know that because my function is of the form c times e to the minus x squared, the value of the function at 0 has to be equal to c, right? But my initial condition here told me that the initial value, y of 0, had to be equal to 4. So that means that y of 0 is equal to c. Y of 0 is equal to c. And y of 0 is equal to 4. So necessarily, c has to be equal to 4. Is that okay?
Yeah, I think.
Please. Yeah. Can I see a show of hands for those of you who understand this? And please, if you do understand it, raise your hand. Okay, I still have Radu, Leo, Shine, Vicente. We're all still good, okay.
But miss,
Yeah.
what does this have to do with what we learned yesterday?
This is how we're going to solve the equations, okay? So we need to verify, like yesterday we started modeling things. Today we're starting to look at how, like what it means to solve differential equations. And then on Monday, hopefully we'll be able to actually model the problems and then solve the problems.
So we're gonna put it together like in
Yes, definitely.
Okay.
All right, so then I'm going to have, okay, so if you understand this, I'm going to ask you to, I'm sorry, I really think I'm not being too clear today. Hopefully I will get a little bit better. So example, remember that we said, okay, we said that y, which was equal to 3 over 4 plus c over t squared, was a solution of 2 times t times y prime plus 4 times y is equal to 3. Okay, so this is the second example that we did earlier, in which we verified that this was a solution of that. Okay. Galen, do you have a question? Okay, that's a no. So we had that this type of function was a solution of this type of problem, right? So this was a general solution because it still has a constant that is not fixed, whereas this is just my differential equation. What I'm going to ask you to do now is to verify, to solve the initial value problem, where 2 times t times y prime plus 4 times y is equal to 3, and y of 1 is equal to -4. Okay, so you already know that your solution has to have this form. Now what I need you to do is to find the one value of c, this constant that we still haven't found the value for. Find the value of the constant c that will make this be equal to -4 when y is equal to 1. Raise your hand, please, if this is clear. Okay, so the idea is to mimic more or less the problem that we had just before. So you have to find the value of c that will make this also verify the condition that y equals 1 is equal to -4. Okay, I'll give you 2 minutes to solve this problem. All right, who's done? Raise your hand, please. Okay, so let me give you the solution for this one as well. You have that y is equal to, so when t is equal to 1, the function that you find is going to be equal to -4, right? So that means that the function, which you know has to be of the form y is equal to 3/4 plus c times t squared, you're going to have to evaluate that at 1. So we know that the function has to be of the form 3/4 plus c over t squared, right? So because this is the general solution of the equation, of the differential equation, right? Now, when y is equal to 1, I can plug this value of 1 into the value for the function that I have. So that means that I'm going to get 3/4 plus c over 1 squared, which is just equal to 1. Right? That means y of 1 is going to be equal to 3/4 plus c. Does everybody understand that? Can I see a show of hands for those of you who understand this? Okay. So now I also have that y of 1 is equal to -4. So I can set this equal to that. But because I know that y of 1 is equal to 3/4 plus c, and y of 1 is equal to -4, then these two things have to be equal to one another, right? So if I want to solve for c, I just have to make these two expressions equal to one another. That means I'm going to have 3/4 plus c be equal to -4, which means that c is equal to 4 minus 3/4, -4 minus 3/4, right? And so that's -16/4 minus 3 is -19/4. Can I see a show of hands for those of you who understand this? Okay. So I have now that c is equal to -19/4, which means that the particular solution to the full initial value problem, so initial value problem, which is of course the differential equation and the initial condition, is the function y is equal to 3/4 plus c, which is -19/4, so -19/4, and then times t squared at the denominator. Does everybody understand this? Yeah, really. All right, Juliette, your hand is up. Is that a mistake? Okay. Do I have any questions, or is this okay? All right, so we have that essentially. Just let me give a summary, hopefully to clarify some of the things. Today, so yesterday, we started talking about differential equations. Right? Yesterday, what we did is we started modeling given real life situations. What we've been doing today is we've been learning how to verify that a function satisfies a differential equation. And then we have learned how to determine if something is a particular solution of an initial value problem, right? So then find a particular solution. Of course, as long as we are given the general solution, right? So in both of the problems that we just solved, we had been given the form of the general solution, and what we found was just the particular solution by plugging into our initial condition, right? So these are the three things that we know. Verify that a function satisfies a differential equation, and then find a particular solution if you're already given the general solution. The big problem over here is that we still don't know how do we find the general solution, right? So how do I find what function is actually going to satisfy the differential equation? Is everybody following? Yeah. Who's following? Raise your hand. Great. Okay, that's good. Lots of hands up. I like that. Okay, so today I'm going to start the very beginning of how to solve differential equations, and we're going to get a lot of practice on Monday, but I want you to get an idea of where we're going with this and how it links to what we did yesterday. Okay, so we're going to start with the model that we started yesterday. So example. And the first example that we talked about yesterday in modeling was unrestricted growth, right? So unrestricted growth. Juliette, your hand is up. Is that because you forgot? Okay. So in unrestricted growth, we said that if we have a population, then the population is going to be growing at a rate that is proportional to the size of the population, right? So we said the derivative of the population size with respect to time. So the population is growing, the population is changing at a rate that is proportional to the size of the population, right? So this is the first thing that we said. Another way of writing this was that the derivative of a function is equal to some constant times the original function. Okay. Now, is there anyone in the class that has any idea of a function that is such that when you differentiate that function, you get the same exact result, but with a constant in front? So this is what this means, right? We have that in this equation, we have that if we differentiate the function, we get the same function that we had originally with a constant in front. Right?
E of x?
E of x, almost exactly, but in a more general way. So if I have, for example, that the derivative of a function, suppose that you have that the derivative of a function is equal to 3 times the original function. So if I had that the derivative of my function is the same function but with a 3 in front, what would you have? What would the function be in this case? The idea of e to the x is right, but it's a little bit more complex than that. If there's a 3 in front, where does that come from?
The constant multiple rule?
So the constant multiple rule would tell me that the derivative of 3 e to the x would be equal to 3 e to the x. And that just means that the derivative is equal to the original function, right? So it's not quite the same. Now what I want is for the derivative of the function to be the same function that I had originally, but now a new piece has appeared, which is a 3 in front of my function. What could this be? So listen to what I'm saying. You have the same, so the derivative is the same function, but now it has been multiplied by a constant.
X to the 3?
X to the 3 is going to be, so if I have x to the 3 prime.
No, like E x to the 3.
Oh, e x to the 3. Okay, so we're getting there. E x to the 3, if I differentiate that, I'm going to have 3 x squared e to the x to the 3. So that's almost the same thing, except I also have an x squared in front. So that's not really gonna cut it for us.
It's 3x.
3x, yes. So it's going to be e to the 3x. Right? Because if I differentiate this function, I'm going to get the same exact thing, but because of chain rule, I'm going to bring the derivative of the inside, which is 3x. And so the derivative of the inside will be 3, and that will be multiplying my function. Does everybody understand that? Can I see a show of hands for those of you who understand? Okay, so for now, I'm just going to say, all right, it looks like if I have that the derivative of my function is some constant times my original function, then this looks like it's going to be satisfied by a function of the form p of t is equal to e to the power of k times t. Okay? So this is what I should have. E to the power of k times t, because I know that when I differentiate this, a k will come in front, and then I will still get the original function, right? So this is just from looking at the function, our intuition, and after a lot of thinking, we have gotten to this. I'm going to say there's actually a constant in front because the constant is not really going to change much. Of course, we don't know this yet. We have to show this. So the whole idea over here is to say, okay, how can I show that this is actually true? How can I make sure that this happens? Does everybody understand why this function should be a solution?
What's the A?
It's just a constant for now, right? Because,
Same thing as
I'm sorry?
K? Same thing as K?
Yes, so the thing is that k is already a value that is given to us. So for example, in this case, you would have that k is equal to 3. But for example, here, e to the 3x would be a solution, but also 4e to the 3x would also be a solution, because then you'd be multiplying the left-hand side and the right-hand side, so nothing would change.
Okay.
Okay, so that's going to appear for now. But for now, what we can say is, okay, it looks like a function of the form e to the k times t is going to be a solution to this problem. We can see if there's anything else that we can get from this. Do I have any questions? Okay. So now, in what's remaining of the class, hopefully I'll just be able to solve this problem, and then I'll let you go. You'll have just one problem to, I think 2 problems to solve during the weekend, and then on Monday we'll elaborate on this.
Is the web work still due Friday?
The web work
Today?
is still due today. Yeah, so that's only partial fractions and trigonometry.
But I put in a good answer, and it doesn't let me like submit it.
Okay, we can talk about it at the end of class. Is that good? You can stay while people leave the meeting, and then I'll answer whatever question you have.
Yeah.
Okay. All right, so what we have is dp over dt is equal to k times p. And we're going to try to solve this equation for now. Okay, this is our goal for the rest of the class, and then after that, we're done. Now, if I try, so the first thing that I should try if I have a derivative is to try to integrate both sides and see if I can get something, right? So let's try that first. The first thing that I could try is, okay, I have that dp over dt is equal to k times p, the function p, and the thing that's unknown in this case is the function p, right? So the first thing that I'm going to do here, I'm going to integrate both sides with respect to dt. And so I get, on the left-hand side, I get the function p. And on the right-hand side, I have to integrate kp with respect to t. Wow, this doesn't really work, right? We don't really have a way to evaluate this integral yet because we don't know what the function p is. This is the thing that we're trying to find. Can you raise your hand if you understand why this is a problem? Yeah, so if we try to just integrate both sides, on the left-hand side, we'll be able to say, okay, this is actually just the antiderivative of p, of dp over dt. But on the right-hand side, we don't really know how to integrate the function p because that's the thing that we're trying to solve. This is not a constant, this is a function, right? So this is not going to work. In this type of case, we're going to use a little trick. Okay, so what we have is that my variable p, the population, is varying with respect to the variable t as k times p. Like this. Now what I have is 2 variables, right? I have a variable t, which is time, and a variable p, which depends on the time, right? So the population is a function of time. So the 2 variables are linked. But I can interpret this as being 2 variables. And what I'm going to do is I'm going to try to separate these 2 variables and integrate with respect to each one of them separately. So I'll try to find an expression that only depends on p, integrated, and then an expression that only depends on t and integrate that, okay? So if I'm going to integrate with respect to t, I'm going to need a dt. So I'm going to multiply that on the right-hand side, okay? So I'm going to try to integrate with respect to each one of my variables separately. This is the big idea over here. I'm going to have that dp is equal to k times p times dt. Does everybody understand that part? Yeah, so I'm just multiplying with respect to dt. I'm saying, okay, over here I have the variation in p, and then I'm going to compare it with the variation in t, right? Because now I'm considering them just as two variables. Then I'm going to try to figure out a way to write this equation in a way that there's only p's on one side and only t's on one side, so I can integrate the terms in terms of t separately from the things that I want to integrate with respect to p. So on the left-hand side, I have dp, but now in the right-hand side, I have p. I don't want that. I want p to be with the p and t to be with the t, right? So that means I'm going to get dp. And if I want this p to be on the left-hand side, of course, I can't subtract it because this is not being added. I have to divide both sides by p. And so I have dp over p, and then this will be k times dt. Do I have any questions? Just like a big question mark in general. Okay. All right, so now I have an expression on the left that is just in terms of p, and an expression on the right that is just in terms of t, right? Now, again, why do I want to do that? Well, so why do I want to do that? That's because if I have just an expression in terms of p here, and then I have an expression in terms of t here, then I'll be able to integrate each one of them separately, right? And then I'll have, hopefully, a way to find just p as a function of t, which is our ultimate goal, right? We want to solve for what the population is going to be at any given time. All right, so this is what I'm going to do. I'm going to take the integral on both sides. Questions here? Okay. Now, if I want to integrate dp over p, so this is the same as integrating 1 over p with respect to p. Okay. And on the right-hand side, I'm integrating the constant k with respect to t. What is the integral of 1 over p with respect to p?
Ln of p.
Ln of p. Yeah, so on the left-hand side, I'm going to have ln of absolute value of p. Okay. Actually, this is not going to be that much of a problem because we know that the population can only take positive values, right? So it should work regardless, but we are going to make it mathematically correct. So it's ln of p. And on the right-hand side, what is the antiderivative of a constant with respect to t? So it would be t, right? So the constant times t, that's what Juliet said over here. So if I have, for example, the antiderivative of 2, it would be 2 times t. Or if I have the antiderivative of pi, it's pi times t. So if I have the antiderivative of a constant k, it's going to be k times t. Right? So k times t. Does everybody understand that? Can you please raise your hand if you understand how I integrated each of the sides? Okay, so I have 12 participants at least. Hopefully this is the case for everyone. Yes?
Sorry, how is it k times t and not t again?
Because you have that the integral, for example, of 4 with respect to t is just 4 times t.
Mm-hmm.
Right? So if you have the integral of k times t, then if you have the integral of k with respect to t, then it's going to be the constant k times t.
Okay, thanks.
Okay. Yeah. All right, so this is what you have. Now there's just one little thing that we forgot, which is a constant of integration, right? So we need to make sure that we add that constant of integration, and I'm only going to add it on the right-hand side, right? And that's because if I add a constant on both sides, then it's the same as adding it just on one side, because I would just move the constant on the left-hand side to the right-hand side anyway, right? So I'm just combining both of these constants of integration on the same term. All right, so I have that ln of p is equal to k times t plus c. That's great. That means that I now have not the derivative of p. I have an actual expression in terms of p, and now I have to figure out how to find just p of t. So like p as a function of t. Now, if I want to solve for p in this case, what would I have to do? This is going back to high school.
Is it like ln of kt plus c over ln of p?
Not really. So what we need, what I'm looking for is to figure out what function will get rid of this ln on the left-hand side. Does anybody know what the inverse of the logarithm is?
E?
E, right? So if I have e to the ln x, that gives me just x, right? In the same way that ln of e to the x gives me x. So if I want to solve for p over here, what I can do is I can raise each of the sides to the exponent of e. So I'll have e to the ln p on the left-hand side. And on the right-hand side, I'll have e to the kt plus c. Can I see a show of hands for those of you who, now that you have been reminded of this, remember something like this coming up at some point during your high school? Okay, that's not that many hands. I need more hands to be convinced that you know. Okay, so this is going to be crucial to remember when we're solving for things. Okay, you need that rule. Okay, and now I'm just going to simplify this. I'm going to say, well, it actually, e to the ln p just gives me p. And then on the right-hand side, I can say this is e to the k times t plus c, but plus in the exponent is the same as multiplied outside of the exponent. Juliette, did you forget to lower your hand, or do you have a question? Okay. Okay. So now we have that p is equal to e to the k times t times e to the power of some constant. But this term over here is just e to the power of some constant. So that, like, this constant can take any possible value that we want, which means that this term over here is just going to be denoted by some other letter, right? There's no reason why I need to keep that as e to the c. So I can just denote this by the constant a. And this means that p is going to be equal to some number a times e to the kt.
Oh shit.
I don't know if that was surprised about this, but if not, it was a suitable moment to say that. All right, does this work for everyone?
Mm-hmm.
Yeah, okay. All right, so then what this means is we have that the population is some constant times e to the k times t. So I'm just going to go back to what we discussed about, what we talked about yesterday, just to kind of make the link between the two things. And then you'll have homework, but the homework will be just about the first part, because we are going to need a little bit more of examples before I leave you to do this on your own. So yesterday we said dp over dt is equal to k times p, right? And what I just said is if you have this, that means that p of t has to be equal to a times e to the k times t. But yesterday, we said if I have a value of k that is positive, then my derivative, my differential equation, let's say if I start at this point, my derivative is going to grow at a rate of k. And so that means that I'll have something like this, right? And it just turns out that, okay, so, and then if I do the same thing, but I started a little bit higher, that would just mean that I would start growing faster before, like this, right? And then if I started lower, then I would start really slow, but eventually I would still get the same result, right? So that means is that all of these possible solutions are of this form over here, where a is a constant that I don't know yet. And how do I find that constant? Well, I'm going to find it by using the initial condition and then solving for the value of the constant. Depending on what value you have at the initial time, you're going to have a different constant in front of the function, and you're going to be able to determine the specific solution that is going to pass through that point. Does that make sense for everybody?
The a decides where the
function
where it's going to be
starts.
placed on the y.
Yeah.
Okay.
Yeah. So the k is already fixed. For example, in this case, it would be, I don't know, k is equal to 1. So that's already going to be given to you, or you're going to be able to find it through some other kind of algebra. But the a is what you need to find based on your initial condition. Okay, so this is the constant that will allow you to find that. Does that make sense for everyone?
Mm-hmm.
Okay, so now what you have is a bunch of, like yesterday, we came up with a bunch of differential equations. And now today, what we are saying is, okay, here's the mathematical tools that we're going to need. And in Monday's class, what we're going to say is, okay, all of these models that you created, here's how you solve them. Here's how you find the solutions of those differential equations. Do I have any questions about this?